Okay. So, one, all respectable participant authors in the International Conference on Data Science and Analytics. Okay, sorry. The chairman of this session 3.5B. Uh, I am working a lecturer at Baghdad College of Economic Science in Iraq. Okay, before we begin, I would like to thank all organizers for their fantastic effort in organizing this conference. We have just one notice for all authors. The presentation time is just 10 minutes. Okay, we are going to start with the article ID 97 or word sense disambiguation in the domain of statement analysis through deep learning. Vedant Baju, the first author. Are you here, please? Vedant, Dr. Vedant Baju? Okay. Please, can share your presentation? Okay, your presentation is okay now. Please go ahead.
Thanks so much. So, hi everyone. Today I'll be taking you through a research piece that Shebnem Emmanuel Dufog, and myself, Vedant Beju, have put together. That revolves around word sense disambiguation in the domain of sentiment analysis, and effectively utilizing deep learning to try and solve the problem of word sense disambiguation, or WSD. Before I really delve into the meat of the presentation, I just want to touch on a few focal points that I'll be going through from a flow standing perspective. So firstly, I'll just touch on the scope and background just to get a better sense of the overall research gap. Next, just moving into the data that was utilized as part of the investigation, and the overall methodology, and some of the articulation of the results that we attained as part of the study. And lastly, just the overall conclusions and potential future works that can come out of the study going forward. So if we delve into the background or the scope, I just want to touch on the problem definition on two main components of the study. Number one being sentiment analysis, which I'm sure many of you are familiar with, which is really just a text analytics technique that allows or enables the measurement of an of the attitude of a customer or a particular entity towards something. So I think it's a major component of natural language processing and very familiar in that domain. The next component, which is a big component of this research, is word sense disambiguation, or WSD. And this is really a problem that deals with identifying the correct sense of ambiguous words in a given sentence, and also the context in which words are used can significantly influence their meaning. And the overall research gap that exists, I mean, just blending the two together, whilst many studies actually focus on sentiment analysis as well as WSD, more so in isolation, there's sort of a lack of process that bridges the two together. And this raises or begs to question whether or not previous sentiment analysis studies have actually been correctly predicting the overall sentiment given the particular context that a word is utilizing. And to better demonstrate the concept of WSD, or word sense disambiguation, I've got a few examples here. So firstly, consider the word small. So I've got two domains or two contexts. In the electronics context, I have a sentence here that reads, "My purse is small enough that it fits in my jeans pocket." So typically, the word small in here refers in the positive light, because it really refers to the ability or the mobility that you can actually fit your purse in your pocket or your jeans pocket and carry it around effortlessly. The next domain or next context is sort of the hospitality context. And the sentence that I've got here is or reads, "The hotel room is very small." And typically that would be associated with a negative context or a negative sentiment, just given the fact that we would usually like a larger hotel room. So this really showcases the polarity between two different domains or contexts and how a word can potentially influence the overall sentiment. What I'd like to next illustrate is another sentence that reads, what's also within the electronics context, is sort of relating to a vacuum cleaner. So the vacuum cleaner really sucks. So although a very colloquial word, but sucks could have two types of meanings and creating some level of ambiguity here. Number one being the suction. So it actually could be positive in that sense, because the vacuum cleaner is actually doing its due diligence and performing at a high suction power, or it could actually refer to unpleasant, therefore creating some level of ambiguity within the sentence. So I think we end up with a sort of human versus machine dilemma. I think for humans it's quite effortless to distinguish sentiments and also disambiguate a particular word within a given context. However, for machines it's a bit more difficult. As such, there's a number of algorithms and a number of studies that have come to play, and with the advancements and the build-up of deep learning over time, we do have multiple ways in which we can obviously combat the problem of WST within sentiment analysis. And research has shown that deep learning and specific focus on 1D CNNs and LSTMs, or long short-term memory, actually provides much more superior performance than traditional based machine learning, as well as knowledge-based methods. And this gives rise to the overall research aim of this particular piece of work, which is really to explore the task of word sense disambiguation in sentiment analysis, sort of for a two-class problem, either predicting positive or negative, and utilizing 1D convolutional neural networks and LSTMs to actually resolve or solve the problem of WST. The next slide really just depicts the data set that was utilized. So for the input data, we utilized a publicly available data set, which is the Amazon product reviews data set that essentially encompasses reviews for different product categories. So I think there were about 10 product categories. We've utilized 3, fashion software, as well as grocery and gourmet food as the selected categories. In terms of how the data looks, so what you see here is basically an overview of the data, whereby your product category is essentially the context in which the review is relating to, and the rating is effectively the sort of feeling towards a particular product that was purchased. And the rating scale ranges from 1 to 5, with 1 being the worst and 5 being the best. How we've structured it from a sentiment classification, we've assigned ratings 1 to 3 being negative and 4 and 5 being positive. In terms of the overall methodology that was applied for this research, so we've broken it down to a few steps. Number 1 being the overall data pre-processing. So here we've applied a number of text pre-processing steps to the Amazon input data set. Number 1 being encoding of the context category, as well as creating those sentiment buckets, positive or negative, then converting the review to lowercase, tokenization of that, removal of your stop words and punctuation, and lastly, the synset enrichment, which allowed us to get an overview of some ambiguous words based on their parts of speech. Next was to utilize a pre-trained embedding, which was glove embeddings that allowed us to sort of fast track the model build process and vectorize the input words. or the input text. And the third step was really for the model experimental setup, in which we've just highlighted the parameter configurations for training, as well as the CNN and LSTM architectures. And lastly, just understanding how we've measured the performance. So we've looked at a few metrics: accuracy, precision, recall, F1 score from a statistical standpoint. And lastly, the wall time being the computational metric, just to allow us to assess the cost to benefit ratio for the various algorithms that were implemented. I think an important note to make here is that we've utilized 95% t-stat confidence intervals, and this is just largely due to the fact that we've run the various models in 10 run samples just to obtain our results more effectively. In terms of the model experimental setup, so we've split this into two phases, one being the baseline model comparison. So for the baseline model comparison, we've initially looked at CNN, so looking at a model that has no context as input and only the review as input, and then comparing this to a 1D CNN model that has two branches, one branch referring to the input review as the input, as well as the second branch looking at the context as input. And then after which, just comparing the best model from there with the LSTM context-aware model to better understand how does the performance fare between the two methodologies. And after which, we've decided on which model was the best. We've essentially applied some hyperparameter tuning to better get a sense of what parameters could influence the out of sample performance of the best model. So essentially, we've looked at including an additional dense layer to the second branch. We've increased or adjusted the dropout percentage from 0.5 to 0.8, changed the flattening layer to global max pooling, and then also included or encompassed a bit more 1D CNN layers just to understand the impact of that, and also removing max pooling and then potentially adding it back just to see what was the significance of that. And the table that you see lastly is just effectively the training model configurations that we've applied for our training process. The next slide really dabbles into the baseline architecture of the 1D CNN model with context.
Please, you have just 2 minutes, okay?
2 minutes. All right, thank you. So the architecture here is effectively showcasing two branches. The one branch obviously having the input review data, and the second branch, which is the context category input, and effectively concatenating both endpoints into creating a fully connected network in which we have an output which relates to the probabilities, but governed by a predictive threshold of 0.5 to get the sentiment predicted categories. From a results and discussion standpoint, we looked at the effect of context as an input in WST utilizing two context categories, which was fashion and software. And what we see from a baseline comparison is that the CNN context-aware model proves to be far better than both the CNN model without context, as well as the LSTM model with context. So as you can see across the board, the 1D CNN context-aware model proves to be much more superior from a statistical standpoint, as well as a cost-to-benefit ratio, whereby the LSTM model took about 15 times longer than the CNN 1D context-aware model to effectively generate an output. And this further illustrates that the LSTM model is much more computationally expensive. From a hyperparameter tuning results, what we've looked at is basically all of the parameters that we've discussed earlier. And what you see here is the F1 score, the validation F1 score, and the associated box plots for the various models. What's important to note is that the addition of a dense layer didn't really improve the overall performance of the model. Whilst we did include global max pooling, it did hold a higher F1 score, but I mean the range is quite wide, which doesn't really make it that favorable. the dropout percentage model, or the adjustment of the dropout percentage model, did prove to be slightly more significant, as we observe a slightly higher average F1 validation F1 score. And then lastly, we looked at the effect of an additional context as input on WST. So moving from 2 context categories to 3 context categories, we basically added in the gourmet food. And what we see here from a statistical performance perspective is that the 1D CNN model still maintains a higher out of sample performance when scaled over the LSTM context aware model. And from a computational standpoint, I mean, still holding on to what we saw earlier, it's sort of doubled in terms of its training time. So from a cost to benefit ratio, it really is superior in this modeling context than the LSTM model. So further showcasing the strength of these CNN models. In terms of just wrapping up the overall conclusions and the future work, so what we've seen and what we've showcased was that the effect of context does have a significant influence on the model's performance to learn associations between words and better predict the sentiment. From a hyperparameter tuning perspective, there wasn't much that we did gather. I mean, whilst we trained on a number of parameters or adjusted a number of parameters, there wasn't anything that significant to say that we could include in any models going forward. And lastly, I mean, from the 1D CNN versus the LSTM context-aware comparison, we did notice that, number one, the LSTM model was far less computationally efficient than the CNN model, thereby allowing the CNN model to have a much more better or robust performance, both from a statistical standpoint as well as a computational standpoint. In terms of the future work that is resulting, number one, the study focused on the overall polarity, which was positive and negative. Sorry, Maz?
Okay. Thank you. Okay. Thank you. Well done. Okay. Your work is very good. Really very good. Thank you. Okay. We are going to next ID, number 23, building deep convolutional generative adversarial network model by using Python for image translation. The author's Crunch.
Yes. Yeah, I'm here.
Are you here?
Yeah, I'm here. Can you able to hear me? Good afternoon.
Yes, you're good. Very well. Hello.
Okay. Yeah.
Please share your presentation now.
Yeah, sure. I'm going to do that. Can you able to see my presentation?
No, nothing.
1 second. Now, can you able to see?
Yes.
Hello.
Okay, go ahead, please. Yes. It's okay.
Yeah.
Okay. Go ahead, please.
Yeah. Okay. Good afternoon. Good afternoon, one and all, and the moderator. Very good afternoon. So my paper discuss on building deep convolutional generative adversarial models by using Python for image translation. I am Dr. Srikanth Ralapalli, and we have our colleague here who is a co-author, Mr. Vishwanathan Shankaranarayan. We are from Boto University, Eswatini, Africa. So let me start my presentation. So I have divided my presentation about the abstract of the paper and introduction, a built introduction, the related work, whatever is already done in this area, and the methodology, what we are following for this deep learning model. And finally, we see a small example of how a small color photographs can be taken for developing the DCGAN, and finally results and conclusions. So this is how I'm going to present it. So if we talk about generative adversarial networks, as if this is a new concept in the area of image translation. So very little work on this have been done for the implementation and configuration. If you particularly talk about a generative model, So for example, this could generate a new photographs of animals that will look like real animals, or it may be something that a model that can be developed to predict the next word in a sequence. So these kind of examples that we normally say that they are generative models. So when we talk about generative models, so we also use certain deep neural networks because it is required for this study. So we also used the convolutional neural networks again, which are the part of the neural networks. So the most important part of this developing GANs, okay, is basically generative adversarial networks. Basically, we use the unsupervised data sets. Unsupervised data sets, any unsupervised data sets can be used, and we can able to train the generative models. So what will happen is when we do this, we will try to improve the quality of the images, especially in our work, where what we have taken the data sets is image data sets. So where we can see that we can help to improve the quality of the images. So whatever we have taken. So particularly in this paper, we are trying to propose and evaluate a deep learning model, which is built with using Keras, and we are also trying to evaluate its application in this article. So we also try to study some techniques where we can, which can help to improve the generative adversarial networks, and also try to implement the algorithm. And finally, we try to develop the DCGAN, that is deep convolutional generative adversarial network models for an unsupervised data sets. So basically, when we talk about these kind of models, so we use generative adversarial network for an unsupervised data set. So we have taken a data sets, an open data set, and we try to understand how these generative models can be applied. So coming to the introduction point, as we all know that deep learning, again, it's a machine learning technique which can be based on artificial neural networks. So we can have the GANs as an approach to generative modeling. So and as I already said in the abstract, that it is an unsupervised learning task of the machine learning. So we are doing. So basically, it's an unsupervised learning task. So any kind of unsupervised data sets can be taken, and this model can be implemented. So what actually happens with the GANs? Why we are using generative adversarial network series? So it has a special ability to learn the regular patterns of the input data. So it means that there are maybe many other models, but they don't have that ability in discovering the automatic of the patterns, regular patterns, but GANs can able to do that. That is why we can use the generative adversarial network. So the model can able to provide a proper output for a particular data sets. So this is why we are using GANs in our study. So coming to the related work, there is some related work done using this, like deep learning model was developed using Keras, that they use the images of the chest X-rays to predict whether the person is normal or they might have some chronic diseases like cancers or pneumonia. So this kind of work has been already done by certain people. And also the new frameworks they have developed, which can estimate the generative models with the adversarial networks. So these kind of work which has been done already. So what we propose is we propose the deep learning model with Keras. Here we develop a deep learning model. So we allocate this work into a different stages. So first we outline our network, and then we collate the network, and then we trim that network. We assess, and finally we have a model which can predict what exactly the data is. For example, I give some data, pictures of an animals, or some kind of text data. So we'll able to predict that what exactly this, or it can give a better picture of what we are trying to provide here. So developing deep learning models with Keras, so we can able to do it in this following ways. So here we have some code which I showed, which we used for functional model with a sequential API. This is a Keras code which we can use. So here we take the deep layer model again, deep learning model, so which will help us for to predict in a better way. So this is some, and this is an implementation of the GAN training algorithm. So whatever the training algorithm is there, we try to use this and the data sets, and we try to implement this one. And we have some data sets. So the data sets, when it comes to the point of data sets, we use the data sets from Keras, that is called as a C10 data sets. So Keras can provide the access to the data sets with the help of a load function. We can load the Keras data sets using this thing. For example, if you see this in this figure, so we have from keras.datasets.c10 import load data. So we are using only that particular statement. Okay, so which will help us to load the particular data set. So C10 is basically having thousands of small color photographs. So color photographs, but if you want to improve that and know that what kind of data set it is, so we need to write an algorithm, and we need to train that algorithm so that it will effectively know that what is the data we are trying to use it here. So this is data set which we are using, and we have defined and trained the model. So you can see that this is the input data what we have seen. So if you see this clearly, we don't understand. Yeah, yes, I'm going to finish it. Yeah.
So is it results section?
Yeah, it's final. Yeah. So this is a result section. Yeah. So I'm going fast. So we are going to define the train the model. At this stage, the photographs is given. And finally, the result section when it comes. So we can't use a CPU here because we need to use the GPU because we are dealing with the pictures here. And so the configuration for this should be a little bit high. Like we have to use the Tesla V100 GPUs, so which will increase the training speed of the model. So we have to use this. This is my results here. And finally, you can see the photographs which we have seen. At least now, after a few stages, we can see the better clarity of the pictures, and we can know that what exactly these pictures are. So this is our results which we have concluded. So it will definitely improve that. So when we take for unsupervised data sets, so we can improve the quality of those pictures, images by writing the Keras, by implementing through Keras. So finally, conclusion. So I say that GAN, that is generative adversarial networks, are used for training the deep neural networks models in practice. And I conclude that these are the best techniques when we are adopting for the unsupervised data sets. These are my references. Yeah, that's all. Thank you, sir.
Thank you very much. Thank you, sir. Okay, now we go the next ID 67, dependency structure-based cognitive data analysis. Serena Chaka.
I am here, hocam.
Okay, tamam. Please share your presentation.
Yeah, I'm sharing my screen right now.
Tamam.
Can you see my presentation?
Tamam. Buyurun
Okay.
lütfen.
Is everything okay?
Yes.
Okay.
Lütfen.
Thank you. Hello, dear participants. My name is Serenay. Today I'm going to present our work titled Dependency Structure-Based Cognitive Data Analysis. In this study, we have worked with Assistant Professor Dr. Fulya Gökalp-Yavuz. Here is the overview of my presentation. I will first start with the introduction part. The human brain has a complex structure. For instance, it has almost 100 billion neurons, and every neuron should pass through almost 10 to the power 15 neurons to communicate with another one. Thanks to the recent developments on brain-computer interface techniques such as functional near-infrared spectroscopy or functional magnetic resonance imaging, it's possible to observe and examine the changes in brain activity of the subjects. As many neural data includes multiple observations taken from the same experimental units, longitudinal data structure is an integral part of many neuroscience studies. In our study, we have utilized data from MBAC test paradigm, which is one of the most commonly used functional neuroimaging study to assess working memory of the subjects. In this data set, also FNIRS modality is used to observe individuals' brain activation while they are performing MBEC tests. At this point, I think it's better to mention what FNIRS modality is. FNIRS is a non-invasive light-based technique, and it can allow us to monitor changes in oxygenation status of tissue. According to Willinger and Chance, functional state of the brain can affect its optical properties, and the concentration change can be measured by FNIRS, as oxyhemoglobin molecules can absorb or swallow some of the light. FNIRS modality also can allow us to obtain information from different brain locations of the subjects through optodes. In our data set, optodes are represented by indices variable. I will move on to data description part. As you can see in figure 3, the subjects are presented with a series of numbers as visual stimuli. In the experiment, participants are asked to respond when the correct number matched with the previously seen in 2 or 3 tries is displayed on the screen during 2 or 3 back conditions. On the other hand, they do not have to memorize any number in 0 back condition. A 0 back condition is considered to be control state to check whether subjects are engaged with the text or not. We did not include the results of this stage during statistical analysis. We have also implemented some data processing steps. We have first convert the optical density measures into HBO and HBR concentrations through modified Beer-Lambert law. And biologically, an increased blood flow occurs to the active brain region, and this station results in decreasing HBR and increasing HBO concentrations. And these two chromophores can be used as indirect indicators of cortical activity. But we have only used HBO concentrations during the analysis, since Hoshi stated that they are the most reliable measures to work on alterations in regional cerebral blood flow. And then we implement Butterworth low pass filter through Butter function in MATLAB. After this step, we have separated the observations corresponding to each block with the help of proc segmentation function. In this table, we can check the variable descriptions. Values represent our response variable, and it includes observations for the mean HBO concentrations. Accuracy is the ratio of correct responses over all responses, while mean response time is the mean response time on each n-back condition, and response time indicates the time that subjects spent until giving response to the specific stimuli. We have also two demographical variables, which are age and gender. MBEC has 3 different levels. Subject represents an ID for each of the 26 subjects. We have also 3 different sessions in the experiment. As I mentioned before, indices indicates the locations of FNIRS channels. We have started with the descriptive data analysis for quantitative variables. By looking at table 2, for instance, we can conclude that values, which is our response variable, can take both negative and positive values. And also subjects are aged from 17 to 33. We can check the distribution of mean response time according to different MBEC conditions for 3 different sessions. As expected from the experiments, the mean response time for 3-back condition is highest compared to the 0 and 2-back conditions, while 0-back condition has the lowest values on mean response time. We have also checked the distribution of mean HBO values according to different subjects. We can conclude a symmetric shape for the distribution of response for some of the subjects. We have checked the relation between each quantitative variable, which are accuracy and mean response time, with response variable, which is mean HBO values, according to different indices. By looking at this figure for a randomly selected subject, we can assume linearity among these 2 covariates. We can make the same conclusion for the relation between mean response time and mean HBO values. I will skip the methods part due to our time limitation, and I will move on to analysis and results part. As a statistical technique, we have implemented linear mixed model. We have started with our full model including all fixed effects. And in this model, we have considered a random intercept term corresponding to indices nested within subjects. And then we have constructed a reduced model after eliminating the insignificant fixed effects. Then we compare these two models. After deciding on the significant one, we have checked we have compared the models with and without nested structure. During the model comparison stages, we have implemented likelihood ratio test through ANOVA function in R programming language. After deciding on the significant fixed effects, we have also checked whether there is a significant interaction among these two covariates or not. At the end of the modeling stage, we have extended our final model with different covariance structures. Here is the summary table for the full model. As you can see, some of the covariates do not make significant contribution to our model. And also, after deciding on the final model with significant covariates and significant random effects, we have checked AIC values for the models, including different correlation structures. As you can see, the model with a general positive definite matrix provides the lowest AIC results. In equation 6, we can check the formula for the final model. In this model representation, user K represents a random intercept for different subjects, while user J given K represents a random intercept term for indices nested within subjects. Also, in our final model, we have M-vector and mean response time as significant fixed effects. We have also implemented hybrid methods which merge linear mixed model with machine learning algorithms. Namely, we have implemented GLMM3, REM3, unbiased REM3, and GP-boost. We have used REM3 function to construct REM3, while REMC3 function is used to construct unbiased REM3. We have also implemented GP-boost with different optimizers, such as we have used gradient descent or weighted least squares, and compared these methods through three model performance metrics. As you can see, although there are not much change on the results of different optimizers, we have selected the one with smallest case, which is weighted least square. Now I will provide the comparison.
3 minutes, okay?
Okay, thank you. We have provided the comparison of the different implemented methods for the case with and without nested structure. In the case without nested structure, we can say that the GLMM3 provides the lowest RMSE, MSE, and Maya values. And we can make the same conclusion for the model with nested structure, as GLMM3 again provides the lowest results compared to the other methods. Now I will conclude our study. Actually, in many previous studies, even the dependence structure was not taken into account. In our study, we have both take the nested structure and dependence structure into account to the analysis of neural data set. We have also controlled type 1 error rate by conducting our analysis with multiple variables simultaneously, which is not the case with many of the previous studies. As a future study, we are planning to implement clustering algorithms to group the observed. Here are our references. Thank you for your attention. If you have any questions, we will be glad to answer them.
Çok teşekkürler. We have ID 153, use of visualization and quantitative image analysis method for tissue characterization in animal models of metabolic disease. Elena Konstantina. Elena? Elena? Elena, are you here? I think. Okay. We go to the last ID, number 6. The utilization of machine learning techniques in diagnosis breast cancer. Ala فمعد visual. I will share my screen now. My presentation is okay.
Yes, sir. Yes, Mr. Mad. We can see your presentation.
Thank you. Okay. The article entitled "The Utilization of Machine Learning Techniques in Diagnosis of Breast Cancer", author Ala Khalifa Ma'at Nassim Najwad. Computer Techniques Engineering Department, Baghdad College of Economic Sciences, University, Iraq. Mijwal is working as a lecturer and academic member of staff in the Computer Techniques Engineering Department at Baghdad College of Economic Sciences, University in Iraq. He has more than 80 publications, and he is working reviewer and editor in more inter and national journals. Outline of this presentation is include introduction, materials and methods, result and discussion conclusions. In this introduction slide, breast cancer is one of the oldest and most common diseases among women. This disease is a severe disease resulting from abnormal proliferation of breast cells that from a malignant tumor that grows uncontrollably. It's the most common type of cancer that can affect any woman. The chance of severe increase with the age, especially after the age of 50. Also, this disease happens with the uncontrolled proliferation of the milk producing that make up the milk duct into breast tissue. In fact, breast cancer accounts for 33% of cancer in women and 20% of all cancer patients to die. This figure shows the surgical methods to remove minimal cancer from the breast in women. Machine learning techniques have been designed in a way recently, particularly after the spread of COVID-19 pandemic. And this technique have become a way of distinguished expert in the field of prediction and diagnosis, especially detecting the breast cancer in mammograms. In medical labs, it is preferable to use machine learning technique to classify image faster and give accurate results that help make decisions. These results are shared with the doctor to take necessary action regarding the disease. Also, healthcare workers can employ machine learning technique to help verify their diagnosis and take the data from the patient faster with a better accuracy. It is expected this technique will be integral with the part of clinical and hospitals in the future. Machine deals with the big and structured data, for example, image, electrophysical data, genetic data, and textual data. Machine learning techniques help to collect the feature of patient and integrate information to determine the possibility of a mass in the breast. Then the text converted into structured data can be read automatically and select the type of disease, benign or malignant. In this work, we have used 5 techniques: artificial neural network, naive-Bayes, K-means neighbor, support vector machine, and random forest are applied to 2 different data sets collected from Kika platform. This platform is very important and free access. The first data set consists of 596 records with the 30 features, and second data set consists of 569 records and 5 features. result and discussion, we have two tables. Table 1 showed the practice of 5 techniques on the first dataset. We focus in the accuracy column. We notice the artificial neural network has very high accuracy, 97.14, while the worst practice is naive phase has 88.12 accuracy. In the second table, we notice the artificial neural network has 92.74% is the highest accuracy, while naive phase has 86.10% accuracy. Table 3 and Table 4 show the confusion metrics of the performance of the artificial neural network. First dataset, we have true positive 83, false positive 2, false negative 5, true negative 24. While in Table 4, true positive 25, negative false positive 1, false negative 1, true negative 87. In this work, we have high accuracy in artificial neural network, and for the first data set, more than 97. And for second data set, achieved more than 92%. The worst performance is naive-phase technique, which has achieved more than 88% accuracy for the first dataset and more than 86% for the second dataset. Artificial neural network, the practice is most acceptable. The practice of random forest is good. The practice of super vector machine is excellent. Nearest neighbor is very good, while naive phase is worst. Thank you. Okay. Elena, okay. Okay, we have finished this session. Okay, thank you for being with us.
Thank you.
In this wonderful fall. We hope see you next year with the new works, inshallah.
Thank
Good
you, sir.
luck,
Thank you so much.
And
bye.
Goodbye. Goodbye.
Goodbye, sir.
Thank you.
Yeah, thank you.
Goodbye.